Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 38. We were talking about the force circle diagram or the merchant circle diagram, and we had drawn this particular diagram in the last module and tried to correlate the various angles and the forces which are involved in the chip formation process. I am going to now today write the different components of the forces and the force balance equations which would involve from this. The first equation I write here is that Fc equals Fs cos of phi plus Fn sin of phi. Let us see in the diagram how I have formulated that. So, Fs cos of phi is basically this right here, and cos of phi is the component towards the Fc direction, and again the Fn, which is actually this particular force right about here, has a same kind of a 90 minus phi direction when we talk about the normal vector. So, along the Fc direction, the component of Fn that will work is Fn cos of 90 minus phi, that is Fn sin phi. So, basically we have Fs cos phi plus Fn cos of 90 minus phi, which is actually written down again as Fs cos phi plus Fn sin phi. So, I am not going to get into the sort of how this, I mean only this one relationship. From this one relationship it is clear why we are recording Fc in terms of Fs and Fn, or how we are recording Fc in terms of Fs and Fn in terms of the angle. So, there are many other angular relationships available in this diagram. I am simply going to write down all the force balance equations. So, the second equation then would be Ft equals Fn cos of phi minus Fs sin of phi. Please be very careful about the directions. So, just in case of the Fc, you had seen that the component of the force Fs is in the same direction along the Fc is the same direction as the component of the force Fn along the Fc. Okay. So, in some cases it may be opposing in nature, and so you have to be very careful about these signs of the force balance by the various components which would be in different directions. We can also calculate the friction force F in terms of Fc sin of alpha plus Ft cos of alpha. We can calculate the normal reaction N as Fc cos of alpha minus Ft sin of alpha. We can calculate Fs as Fc cos of phi minus Ft sin of phi, calculate Fn in terms of Fc sin phi plus Ft cos phi, so on and so forth. The resultant reaction R can be recorded as Fs divided by cos of phi plus lambda minus alpha. If you can see here, this right here is lambda minus alpha, and you have an angle phi here plus lambda minus alpha as this total angle, and what you are doing is essentially you are resolving the R cos of phi plus lambda minus alpha, R being this particular vector. So, you are resolving this vector in this direction, Fs direction, and that is the Fs. Okay. So, here is where you have a relationship between R and Fs. We can also derive a relationship between Fc R cos of lambda minus alpha. We can derive a relationship between Ft, which is equal to R sin of lambda minus alpha. So, please look again carefully at the various angles which have been illustrated in this figure and try to figure out from 1 to 9. I have already told you about 1, I have already told you about 7, the remaining I would like you to actually figure out how these angular relationships are. So, having said that, the measurement of Fc and Ft is easily done with the help of a tool dynamometer. So, typically you can actually either embed the dynamometer onto the surface of the tool, or you can just mount the tool over the dynamometer. Okay. So, that way you can have an average data of the total amount of cutting forces and the tangential forces in the cutting zone. Obviously, there are the small micro sensors or micro dynamometers which can actually be able to gauge what is the kind of distribution of the forces at the cutting zone by just embedding the system just below the rake face, so that you can have a real measurement of the forces along the rake face. So, once Fc and Ft, that is the cutting force and the tangential force, have been experimentally found, Fs, Fn, F and N, that is the shear force, the normal force along the shear plane, the force of friction and the normal reaction along the tool rake face, can easily be determined from earlier equations 3 to 6, which is represented here. You can see this equation 3 to equation 6, and so these are all the relationships between the various cutting forces and the tangential forces with respect to the angles that they formulate in the direction of the friction force, direction of the normal reaction, of the shear force and of the normal force along the shear plane. Okay. So, having said that, the mu friction angle, which is F by N, and you can also write it by as tan alpha or tan lambda, is actually equal to the relationship between Fc sin alpha plus Ft cos of alpha, which is actually how the F is described, the friction force is described, divided by Fc cos of alpha minus Ft sin of alpha, in the way that normal reaction along the rake face is defined of the tool. So, let us call this equation 10. And basically the idea is that if we want to really estimate everything in terms of cutting power, I should be able to also involve a material property aspect here, because obviously the material is now taken to the yield stress value for it to start the flow of the material. Okay. So, therefore, we have to see what is the ultimate yield strength of the material and somehow plug that as a material property into this whole modeling, so that I can get the power consumption of the cutting as an estimate of the various material components which are there, or material properties which are there of the workpiece or the tool, and also as a function of the various geometries like the uncut thickness, the cut thickness, which defines the shear plane angle, and the rake angle of the tool, which are thereby important for all the machining processes. So, we should now be able to correlate these forces to material properties such as ultimate shear stress, we will call this tau s. Obviously, once this value is reached, the chipping formation or chipping process will start to happen, and the chip will start to plastically or to separate from the workpiece. The shear force Fs along the shear plane can be written as the amount of area of the cutting zone, which is actually the width of the workpiece times of the uncut chip thickness T1, let us look back and see what we mean by that. So, there is a shear plane formulated in this particular direction, and we are having a uncut chip thickness which is round about this thickness right here. Okay. So, this is T1, that is this point, how much away it is from the zone of machining on the vertical axis. So, obviously, the total area that this particular plane would have multiplied by the ultimate yield shear stress would actually define the amount of shear force that is necessary to separate the chip from the workpiece material. So, the component of this T1 here, this particular thing here along the shear plane, okay, is basically T1 by sin phi. So, this is T1 by sin phi, and if I assume the width of the cutting zone of this particular zone as coming out of the page or going into the page as W. So, this is the total area that this particular face would have. So, T1 sin phi, T1 W by sin phi is the total area that this face would have, and we will be left with the total shear force necessary as W T1 by sin phi, that is the area of the shear plane times of the ultimate shear yield stress of the material, which is a property of the material, and it defines the extent of cutting forces that has to be applied for the material to start machining off or peeling off from that area. Okay. So, this is how you define the total shear force. Okay. So, I will just mention this, that here the W is the width of the workpiece under the chipping zone, you can say, and T1 is the uncut chip thickness. So, from earlier equations 7 and 8, as you can see right here, 7 was related to how the resultant varies with respect to shear force, and 8 was how the cutting force varies with respect to the resultant. We can write the total amount of cutting force Fc as Fs cos of lambda minus alpha divided by cos of lambda plus phi plus lambda minus alpha. Okay. So, obviously, you have to put the value of R here. So, Fc becomes equal to Fs times of cos lambda minus alpha divided by this whole term cos phi plus lambda minus alpha. So, once this Fs is now defined by the earlier process here with the material property and the geometry, I just plug this value here, so that it is completely independent of the forces. So, let us see how Fc then varies as. So, we have Wt1 tau s times of cos lambda minus alpha divided by sine of phi times of sine cos of phi plus lambda minus alpha. Or in other words, I can write the Fc as completely independent of all the other forces and only related to the material properties as Wt1 tau s cos of lambda minus alpha, and this term right here can be written as sin phi cos of phi plus lambda minus alpha. So, we will now perform an optimization here, because obviously the power that is consumed is also the force velocity product, and the cutting force that the tool is applying on the workpiece or the workpiece is applying back on the tool is given by this Fc, which is now related to all the material properties and geometry properties. So, we are going to now do some kind of an optimization in the next module, where we will talk about how power consumption minimum criteria could actually result in a relationship of the various geometries that we have considered, corresponding to which if we operate always the power would be the optimum best. So, with this I would like to end on this particular module, and in the next module we will do this optimization of power of cutting. Thank you so much.